Okay, so we're back here continuing to talk about fluid mechanics, and in the previous video I'd made a video talking about pump curves and showing how you can use a pump curve along with information about a pipe system to figure out how much flow rate and how much head loss and how much power would be required to pump water. And so in this video I want to do a similar example, but I want to look at air movement instead of water. So it's really the same kind of idea, but it's good to see a different fluid to understand how that's different. And so with pump curves for water, you have a pump curve given by the manufacturer. With air, you have a fan curve. So here's like an HVAC system schematic that we're looking at. And there's air that's pulled in here, and there's a fan that's pulling the air through and then discharging it over here. And we want to know how much flow we're going to get. And we're supposed to get 600 CFM. That's required for this particular system, and we're supposed to see, is that going to work given this information about the fan. And so the fan curve, like a pump curve, is going to tell us how much head there is required, or how much head a fan can give us at different flow rates. Okay, so here we've got the flow rates in cubic feet per minute, or CFMs, and then we've got the head here, and it's given in inches of water. So it's so we're going to figure out on this problem the head in air, and then we have to actually convert that to inches of water because air is so light that sometimes it's written this way. Okay, and so these are the characteristics of the fan curve that we're given here, and I went ahead and plotted it in this example so that we can spend time looking at other things. Okay, so here we've got a pump going through here, and we're told that there's going to be a minor loss associated with the inlet and the outlet flows. So there's flow coming in and out, and then we've got 5 bends, and the manufacturer of this particular system has told us that the minor loss coefficient for the bends is 0.21, and the inlet and exit losses for these particular ones are 1.3 and 1.8. So usually you would have to go look information like this up and do some work, and if it's a class, you would have to go find that in your in some kind of table from the book, or notes or whatever. But here we're given all that information. We're also told that the friction factor in this particular pipe material that it's using for this duct is equal, it's got a roughness height that is equal to 0.15 millimeters here. Okay, and so the diameter of the duct here is 0.23 meters, and the total length of the whole thing is 13.4 meters. So that's basically the information we're given, and then we're supposed to figure out what the actual flow is going to be and compare it with the 600 CFMs. Okay, and so we're given here, let's write down the things that we know. So we're told the diameter here is 0.23 meters. This one's in metric, so everything will be in metric. And then the length of the pipe is 13.4 meters. That we're going to need this to do the friction losses. And then we're going to need the density and viscosity of air. We're told it's air at 25 degrees Celsius under the design conditions. And so you would need to then go look up the properties of air. And so I'm not going to show that part, but I'll say that I went and found it, and it was 1.184 kilograms per cubic meter. That's the density of air. And then the kinematic viscosity, nu, it's not a V, it's nu, A, is equal to 1.56 times 10 to the minus fifth meters squared per second. Okay, so these are the properties of air. And then we're going to need the density of water also in order to convert from air to water depth here. I'll show that calculation later. So this is something we're going to need, 1,000 kilograms per cubic meter, well-known number. And then we're going to need the gravity constant. And so we're in metric, so it's 9.81 meters per second squared. Okay. And so we're going to have minor losses. And so I'm going to go ahead and tabulate all the minor losses here first. So we use the K factors, and they all get multiplied by the velocity head to figure out the head loss from minor losses. So we can say the minor losses are going to include the K for the entrance, K for the exit, and then 5 bends, and they all have the same minor loss coefficient. And so here, all that's given in the statement, so I'm going to try to do this whole problem here on this one sheet. So the entrance is 1.3 and the exit is 1.8, and then we have 5 times the bend loss, which is 0.21. And if I add all those up, I get 4.15. That's the sum of the minor loss coefficients. Okay. To get the friction loss, I then need to get the friction factor, and to do that one, I'm going to need the Reynolds number and the relative roughness. And so the Reynolds number will actually change when I'm going through and analyzing different potential flow rates, so that's not a constant number. So I will do that one later. But we're always going to need the roughness height, or the relative roughness, which is the roughness height over the diameter, and that will be the same for any flow rate that we look at. And so epsilon here, we're told, is 0.15 millimeters. And then D, we're told, is 0.23 meters. And then we need 1 meter is 1,000 millimeters. And so to make the units work out, to make this dimensionless, and so I get 0.000652. So this is the relative roughness, which tells us where we're at on the Moody chart, which of those curves that go to the left we're going to look at when we get the Reynolds number at different flow rates to do that. Okay, and so we're also going to need the area. I went ahead and did that calculation separately here, so we know the diameter and the area will be the same every time. So area here is pi d squared over 4. So pi over 4 times the 0.23 meters squared gives me 0.04155 square meters. Okay, so and that'll be the same. These things will all be the same for any flow rate that we look at. And again, the real idea here, like it is with a pump curve, is that we need to look at different possible values for Q and then make a system curve that tells us the energy that is required to move the air through this system. So there's the energy that's required by the system in order to make the movement of the fluid happen, and there's the energy provided by the turbo machinery. And so if it's a pump, then you have a pump curve, and here we have a fan instead, and so we have a fan curve. It's very similar, and it just, again, this is the fan curve here plotted from the table above. Okay, so what we need to do then is we need to come up with our system curve. Okay, so system curve, and we'll say that's from the energy balance. Okay, so we need to do an energy balance here, and like we do with pumps, we start with before the whole system and then we go to the end. And so we're going to have a point here that's a little bit away from the entrance, and then going out here to some point a little bit after the exit. And the reason we go kind of away is so that there is going to be a velocity right there at the entrance, or at the exit and at the entrance. And so if we're imagining points that are a bit away from there, we can ignore that velocity head and just look at the minor loss from the entrance and the exit. Okay, so we've already got a loss that's factored into that one, so we want to include all that in our energy balance. And so looking at those 2 points, then we write our energy balance the same way we always would. So we have P1 over gamma plus V1 squared over 2G plus Z1 is, and then plus the head from the fan. So the head, so the energy at the beginning, 0.1, plus what we add should equal the energy at the end plus whatever was lost. Just simple accounting. And so P2 over gamma plus V2 squared over 2G plus Z2 plus the losses. And those head losses will include the friction and minor losses. Okay. And so in looking at these points here, point 1 and 2 are, now point 2 is definitely higher in elevation in this drawing, at least. We're not told whether it's to scale, but when you're looking at flow of a gas, elevation changes are typically negligible. So if you go into a lake or the ocean or a pool and you go down to a lower depth, you can feel the pressure go up really quickly because the fluid is heavy. In air, if you go up and down, the pressure doesn't change much because it's so light that the elevation change doesn't do much. Now it will change if you go up like in an airplane or up to the top of a mountain, but in like a room, that change is going to be so small it's going to be dwarfed by all the other terms here. So generally for gases, so we'll say for gases, we can ignore, or delta Z is negligible for short distances. Okay. So we'll ignore that, and so that means that our Z1 and Z2 terms can be canceled out, and then because we're far away from the actual intake, far or a little bit away, the velocity at these 2 points is also going to be negligible, so those can be canceled out. And then the pressure, I guess point 2, we will go ahead and include, my mistake, I shouldn't have marked this out. So we're going to say point 2 is close enough here. We're going to go ahead and include that one. All right, so V2 should be included, but P1 and P2 are both going to be atmospheric, so they're equal, and those would cancel out. Okay, and so if we then rearrange all this one, and then for the head loss, if we go ahead and use our Darcy-Weisbach equation along with the friction factors, we're going to say H for the fan should equal to a 1 for this exit velocity. Just make a note there, include this. So we'll have a 1, all these terms are going to be multiplied by v squared over 2g. There's going to be a 1 for the exit velocity right here at the end, and there's going to be loss for the minor losses, and then there's going to be FL over D for the friction losses. So we have a 1 plus sum of the K's plus FL over D. All of that is times v squared over 2g, and that's the velocity in the duct. Okay, so this is our system curve. Okay, and so this thing gives us a system curve, and what we want to do, like you would for a pump, is we want to go through here and plot it and find the intersection point, and that point is will tell us the flow we get and the head. And so we need to then go and get the look at plugging in a few different Q's and into this equation, and then calculating H in inches of water. And I'm going to do one example here, and then I'm going to make a table right here. I'm going to share the results from the first one, and then I'll go through and plug it in for a few different ones. So the table is going to look like this. So we need to look at different flows, and we need to get the H in inches, again, for the system requirement, the energy to flow it through there. So we'll have Q here in CFM, and then for each of those, when we change Q, then we get a new velocity, and that'll be in meters per second. And then we'll need to get the Reynolds number at the different velocities, and then we can use that along with this relative roughness to get the friction factor. And then we can get the H, that is the head, from this equation, and this is going to be in meters. If we plug V in meters per second, this will be in meters, and then we need to get the head in inches of water, inches of H2O here last. Okay, and so the first point, if we look at 0, then the velocity would be 0, the Reynolds number would be 0, friction factor is kind of undefined, the head would be 0, and that's still 0 if you're in inches. Okay, and again, if you put 0 in here, you get H is 0. Okay, so that's our first one. And then I went ahead and did it at 2, 4, 6, 2, 4, 6, 8, and at each of those different, okay, so 2, 4, 6, 7, and 8, because it turns out that it's near there. So I did 2, 4, 6, 7, and 8 for different flow rates. So 200, 400, 600, 700, and 800. Okay, so and then again for each of these, now what we need to do is get V, and it's the exact same calculation each time. So I'm going to do one example here for 200, and then I'm just going to fill the rest of the table out once we've looked at how to do that for the others. And then we can plot that here. We've got our first point, but we can plot the rest of it and figure out the operating conditions. Okay, so here's our system curve from the energy balance. All right, so let's look at, so for Q is equal to 200 CFM, which is feet cubed per minute. We need to get velocity, so V is going to be equal to Q over A, so 200 cubic feet per minute, and then I'm going to convert minutes to seconds, so 1 minute has got 60 seconds, and then I can divide by the area, which I already got up there. Okay, so we have 0.0415 square meters. Okay. All right, so this is going to give me this is going to give me this is in cubic feet per minute, right? And so this is meters. So I need to convert the cubic feet into cubic meters in order to get V in meters per second on this example. And so to do that one, I need to use the unit conversion factor that 1 foot is equal to 0.3048 meters. So this is 1 foot. And then for a cubic foot, I need to cube that. So to make this cubic feet go to meters, I'm going to say 1 foot cubed is equal to 0.3048 cubed meters cubed. All right. And so this will all work out now. That makes this cubic meters, and that makes this second, and then divided by square meters would give me meters per second. And so I got 2.27 meters per second for the velocity here for a flow rate of 200 cubic feet per minute. Okay, so that's the next number in the table, 2.27 over here in the table. And now I can get the Reynolds number. Reynolds number here is equal to dV over nu. And we have D is equal to 0.23 meters, and V we just got was 2.27 meters per second, and the nu we had from the properties of the air 1.56 times 10 to the minus fifth meters squared per second. And if I do all that, I get 3.3 times 10 to the fourth for the Reynolds number, and that's going to be dimensionless. Okay, and so then the next thing I need to do, well, I can fill that out in the table then over here. So I got 2.27, and now we've got 3.3. I'll just put E4. Maybe I should have written this table a little further left. Now I can get the friction factor, which I'm going to do with the Swami-Jain equation. In this example, you could do it. Yeah, it makes sense if you would want to do an example like this in a spreadsheet where you could automate all the calculations. So that means you want to get the friction factor from an equation and not from the Moody chart. So 0.25 divided by log of the relative roughness divided by 3.7. Okay, this whole thing, so it's log of relative roughness over 3.7 plus 5.74 over the Reynolds number to the 0.9. That's the Swami-Jain equation. Okay, and the bottom should be squared. So let's plug that in. 0.25 over log of relative roughness is 0.000652 over 3.7 plus 5.74 over 3.3 E4 to the 0.9, and that whole thing is then squared. So that gives me a friction factor of 0.0247 is what I got for the friction factor, making this big messy substitution. So 0.0247 be next in our table, and then we need to get the head. So now I've got the friction factor and I've got V, and for my system curve up here I've got my sum of the K's and I've got L and D. I've got G, so I need V and F. As Q changes, those two things are going to change, and now I've got V and now I've got F, so I can plug that in. And so we get H fan is equal to 1 plus 4.15 plus 0.0247, and then the length is 13.4 meters over 0.23 meters, and all of that times 2.27 squared divided by 2 times 9.81, and the units on that are going to be meters squared per second squared on the top, and then meters per second squared on the bottom. So the whole thing will come out to be 1.7 meters of air is the head, and that's, again, all this is in air units. So we got 1.7 there for the meters of air, and we need to lastly convert this to inches of water. So H and then inches of H2O is going to be equal to H air, and the way to do that conversion is to just multiply by the density. So H water times rho water should equal H air times rho air to have the same relative change. Okay, so that means that I just multiply this rho air over rho water, and so 1.7 meters times let's see, rho H air, I need to, times 1.184 over 1,000. Okay, and those are both in kilograms per cubic meter, so I'll leave that off. And then this is in inches. The other thing I need to do, or this is in meters, sorry, is convert the meters to inches. And so there are 39.4 inches in 1 meter. So that gets this to inches, and then this does the water to air part. Okay, and so if I do that, then I get 0.081 inches of water. Okay, so this should be 0.081 for the head in inches of water. And so this is at 200, and so here we got 0.1, so a little bit less than 0.1 there at 200. And so I'll fill this out here one row at a time. So 4.54 for 400, 6.82, 7.95, and then 9.09 at these different Qs. And then the Reynolds number goes 6.7 E4, and then 1 E5, and then 1.2 E5, and then 1.3 E5. The friction factor does change a little bit because it's a pretty low roughness pipe, so 0.0221, and then 0.0210, and then 0.0203, and then 0.02, I'm sorry, that was 0.0207. That's not a 3, I can't read my own writing. 0.0204 at the end. Okay, so those are the different friction factors. And in the head, it was 1.7 in the first case, and it goes up to 6.8, 15.1, 20.5, and 26.7 for the head in meters. And then last we have the head in inches, so it was 0.081 for inches for this first flow rate, and then for the other ones it's 0.316, 0.704, 0.955, and then 1.244. Okay, so these are the different head of water. And so again, we plotted the first one there, and then we would need to add these other ones. And so 0.316 at 400 is between those two. So 400 up here, about right there. Okay, so this one's a little bit below that line, and this one is here, and then the next one is 0.704 at 600, and so 0.7 at 600 right there basically, and then at 700 it goes to 0.955, and that's about halfway between those two, so about right there. Okay, and so if you then go and plot this, connect the dots, then you get this curve, and so that means our operating point is going to be right there where the demand from the system, which is the system curve, is equal to the supply of energy from the fan given here. And so you can see that this is going to be at a head of about a little over 0.8, and then the flow rate there is going to be about 630. So we have Q is equal to, or about equal to 630 CFMs. And so remember, our original question was it needs 600, and we got that at 630, so that means that this would work. Okay.